are lots of reasons to visualize data: to inform data cleaning and recoding before analysis, to better understand data structure, to look at relationships between variables, and of course to share our results with others. So far we've looked at how to present data in tables, frequency tables and contingency tables. In upcoming classes we'll talk more about how to describe data using descriptive statistics that measure central tendency and dispersion. But understanding what a table is trying to tell us about the data takes time and a bit of insider knowledge about how to read those tables. They can be pretty dense, and all those numbers might be overwhelming, especially if you don't have time to sit down and really go through them. Consider the difference between attending a spoken 15-minute presentation versus actually having a multi-page report to sit and read and look through. But what about actually using images to display our data? Images are more interesting to look at, and they're particularly effective at communicating large amounts of information very quickly. The human brain actually processes images faster than it can process what it hears or reads. Data visualization as a field has exploded with different techniques and options for displaying data, especially as the analysis of big data has become more and more advanced. You can see some of the best graphic data visualization techniques on display in major newspapers like the New York Times and the Wall Street Journal, which often use large data sets to create interactive data visualizations to help readers understand what's going on. For example, this image is from an article on the impact of vaccines on infectious diseases in the 20th century, where each line is a US state, each square represents a year, and the color is used to indicate the rate of the disease per 100,000 people. The black line shows when the measles vaccine was introduced, and almost immediately we see this drastic reduction in cases. Hovering your mouse over each cell on the website gives you the actual number of recorded cases that year. We won't be diving into such advanced visualizations in this course. We're just going to stick to some basics. First, the most important guideline is that you choose the right type of chart or graph for the data you want to display, as well as for your audience. Garbage in, garbage out applies to charts and graphs as well. You should keep your colors simple, being aware of what is easy to see and particularly how your graph might read to someone who is colorblind. You can use color and contrast to highlight important information on your graph, but remember to be aware of color associations. For example, red can mean bad, high, or hot. Remember how red was used on that chart of infectious disease rates to indicate bad and high? It would be really confusing if that graph were remade with red, meaning lower numbers of cases. No reader would look at that and quickly and easily understand it. So your choice of color is really important. And finally, avoid excessive clutter. Keep your charts and graphs clean of any lines or text that don't add something valuable. This means removing or minimizing grid lines, extra tick marks, extra text, and so on. You definitely want to avoid the use of 3D, which adds visual clutter. There's no reason for this bar chart to be in 3D. It has nothing to do with the data. It also makes it hard to interpret because we can't easily see where the bar stops. Should we read it from the top of the bar that looks closest to us as viewers, or from the back of the 3D shape? This chart looks much cleaner and is much easier to interpret without the 3D effect. How about this bar graph? This is an example from the website Storytelling with Data, which has great information on data visualization. There are lots of things you can do to improve this graph. For example, removing the grid lines and all of those extra labels would help to declutter the graph so that the important information stands out. And the important info here seems to be that the goal time to close deals with this company is a max of 90 days. So how did they do in each month of 2019? I took a stab at it, and this is one solution I came up with. I've removed the grid lines and the labels on every bar because my audience doesn't really need to know the exact number for every month. I updated the title of the graph to be specific to 2019, which allowed me to drop the year from the labels on the x-axis and make that much more simplified. I would actually prefer that it said something like Jan, Feb, Ma across the bottom, but for the moment I just went with the letters. I removed the extra decimal point from the labels on the y-axis because that wasn't necessary, and instead of labeling every single bar, I simply drew a line where 90 would be, because that's our goal, and I just labeled the 3 months that were over that line, because presumably if I'm sharing this information with people in my company, or maybe stockholders or investors, I just want to emphasize these important points. This isn't the only solution or the best solution, but it has already improved the graph in just a few simple changes. So let's start with graphs for categorical variables. Remember that these variables don't have numeric value, they just sort characteristics into categories. The categorical variable types are nominal, which has no order or rank and the category is just different from each other, and ordinal, which does have order or rank to categories such that we can say one is greater than or less than another. One option for displaying categorical data, especially nominal level data, is the pie chart. The pie chart gets a lot of abuse because people often use it pretty poorly. A pie chart with more than 4 or 5 different categories becomes very difficult to interpret because the eye can't easily distinguish the size of each slice and the labels add a lot of clutter. So it's okay to use pie charts, but try to use them for variables that have only a small number of classes. So let's look at this pie chart. Is it easy to understand? Is it pleasing to look at? Can you draw any really meaningful conclusions from it? I guess so we can see that a couple of state populations really dominate, but all of these other tiny slices are barely even visible. The labels add tons of clutter and they're hard to read. Just know, this is not a good use of a pie chart. It's actually trying to show us data on a continuous variable. Those are state populations. So a pie chart isn't even the right choice of chart to begin with. This is bad news. Now this is good. This is location of sales for a company called ABC Enterprises. We can see this as a nominal level measure. We just have the names of different regions. We have just 4 classes: Australasia, Europe, North America, and then the rest of the world. We have nice contrasting colors so we can easily tell one piece of the pie from another, and the labels are right on the slices so our eyes don't have to jump around a lot to make sense of what we're seeing. And of course, the whole pie sums to 100% of all the sales. What about nominal data with more than 5 classes, or ordinal data that has some sort of rank? In that case, we might want to use a bar chart instead. You can use a bar chart for anything you might also use a pie chart for, but the bar chart has more flexibility. It can accommodate more classes without becoming too cluttered. There are also some options like clustered or stacked bar charts that can be used to display bivariate information. For example, here's a simple bar chart. The horizontal alignment in this case is helpful because it makes it easy to read the labels, item A, B, C, etc. You don't want to have labels that are vertically aligned, so if you have long labels for your variables, the horizontal alignment might give you some more space. Then along the bottom we have an amount. So we can see on this graph that whatever item A is, we have the greatest amount, and then the amount decreases as we move from A down through F. And here is a grouped bar chart, which allows us to display a relationship between 2 variables. Again, we have amount on the bottom, and item A, B, C, and D, but for each item we have 2 bars, demonstrating the value for the first and second classes. Let's substitute some actual variables in there so this makes more sense. For example, we might be looking at multiple variables, type of pet, and the time they spent playing with different types of toy. So we have the types of toys on the left side: ball, catnip mouse, bone, and tug rope. Then we use separate bars for dog and cat and use different colors to distinguish them, and the length of the bar indicates the minutes of time spent playing with each toy. So in this single graph, we can tell things like dogs spend more time playing with all the toys except the catnip mouse, which cats spend more time with. The most popular toy for both dogs and cats was the ball. The least popular toy for both dogs and cats was the tug rope. The cats spent longer playing with the catnip mouse than dogs spent playing with the bone. That's quite a few conclusions we can take away from a single graph. You can imagine that trying to glean this information from a contingency table would take more time and not be as visually interesting for your audience. How about continuous variables? One of the most common ways we visualize continuous data is by using a histogram. A histogram looks a lot like a bar chart. It has lots of columns at different heights showing how often values appear in the data. But think back to our problem with the frequency table and the continuous variable. If you had just one column for each unique value, you would have a very long, very flat-looking histogram. Instead, histograms are kind of like the grouped frequency table. They sort the continuous values into bins, which are symbolized with the columns. Unlike a bar graph, histogram columns touch each other to indicate that they represent continuous data, not separate categories. So a 0 to 19 bin includes every value up to 19.99, and it touches right up against the next bin, which starts at 20, and so on. So as an example, here's a histogram of the age variable from our NCVS dataset. We see that age is on the x-axis on the bottom, and the y-axis just measures the count or frequency for each age bin. This histogram gives us an idea of the distribution of our age variable. For example, we can see the minimum is about 16, the maximum looks about 90, and most of our respondents are in their early adulthood to middle age, with fewer respondents over age 70. I've included the table of descriptive statistics in the top corner there to confirm these observations. Here's another example of histograms showing age at sentencing for different types of offenders. So in the case of a histogram, we might want to use multiple histograms if you want to compare different variables with each other. These are univariate displays. Another chart type you might be familiar with is a line chart or a trend chart. These charts typically have continuous data on both the vertical and horizontal axes and are very often used to show change over time. So the x-axis would have some sort of measure of time, like days, months, years. You can also display multiple trend lines on a single chart, which can help compare different categories over time. For example, this graph shows the number of positive flu tests throughout flu season from October to May in 4 different flu seasons, 2016 to 17, 2017 to 18, 2018 to 19, and then this year when we were all dealing with coronavirus, 2019 to 2020. Across the x-axis, we have the months of the flu season, and on the y-axis, we have the number of flu cases. We have a descriptive title that tells people exactly what the takeaway message of this graph should be. It doesn't just say differences in flu cases across 4 years, it specifically said flu season cut short, drawing our attention to how the 2019 to 2020 flu season was different from the others. We can see that we have multiple data series on this graph, one for each annual flu season, but that 3 of them have been faded out. This focuses our attention on the orange line for the current season because that's what we're talking about in this graph. If we just made each line a different bold color, it would be hard for our audience to pick out which line was the important one to look at, and it would also look cluttered and messy. So fading those extra lines to gray really helps make the point here. And finally, scatter plots. Scatter plots are used for bivariate displays with 2 continuous variables. The Anscombe's quartet that we looked at the beginning of this unit was made up of 4 scatter plots. They may or may not include a line of best fit through the points plotted on the graph. We're not going to dig too deeply into scatter plots just yet. We'll revisit them later in the course. But I wanted to show you some examples because scatter plots are just so common. So here's the anatomy of a scatter plot. You can see that you have an x and a y axis with one continuous variable on each. Then you have these gray points. Each one presents a case or unit from your data, and it's plotted on the graph by using its value for variable A and value for variable B as x, y coordinates. Each data point is plotted on the map, and you can see the relationship between the variables start to take shape. You can even see up in the top left corner a data point that doesn't seem to fit the pattern that the other points are forming. This one might be an outlier. Here's a fun scatter plot showing the level of fun that a pet has and the level of effort required to keep it. So for example, right down the bottom there at 0 fun but also 0 effort, you have things like sea monkeys and Tamagotchis and ants. Really fun and low effort is your friend's dog, right? Because you get to have lots of fun with him and then you get to give him back. Lots and lots of effort, not a lot of fun, we have babies, which I can personally confirm, although babies are kind of fun sometimes. And then up in the very top, lots and lots of fun, lots and lots of effort, we have animals like dogs, horses, and dragons. From a scatter plot, you can make some assessments about the relationship between two variables. Again, we'll come back to this later in the course, but here are some common associations, from positive relationships, where both variables increase or decrease together, to negative relationships, where the variables vary in opposite directions. You might see a linear relationship, where the points fall along a straight line, or something more like an exponential or U-shaped relationship. And finally, how closely the points cluster together might tell you the strength of the relationship between these variables. If the points are really hugging a line, the relationship appears quite strong. But if they're spread out and there's not really a clear pattern, the relationship might be weak or even non-existent. We'll be talking a lot more about the direction and strength of relationship between variables in the upcoming weeks. For now, remember to review the reading and lecture material and prepare to apply your new knowledge to making some tables and graphs yourself.